Hi, this is Dane Quinn from the University of Akron. Today's video lecture will focus on gear teeth. In particular, we'll talk about the design of gear teeth and the profiles that they have so that we get good designs for gears. So what does it mean to be a good design? Well, these gears are typically designed so that if the input torque is constant, acting on a gear, so down here over on the left, imagine we've got a torque that's being applied. Then for two gears in mesh, and here I've kind of showed them separated, then the resulting output torque is also constant. So again, there's a relationship, a constant of proportionality between the input and output torques. And one of the things we saw in earlier lectures was that if that's true, then the speed ratio is constant as well. So again, we'd like to design gears so that constant input torque gives us constant output torque. Now, how do we go about designing the gear teeth to satisfy this goal? Let's look at the shapes given here in red. These are sort of candidate shapes for the gear tooth profile. And they have a really interesting, unique, and quite useful property. In particular, right, if I draw the contact normal, right, so that's the normal to this surface, that normal direction is actually tangent to a circle. Okay, fine. The nice thing about this curve, though, is that if I draw a normal at a different spot, say over here, that normal is also tangent to the same circle. Now, why is that important? Well, if I think about the contact force between these two gears, it's going to be directed in the normal direction to the surface. Right? So here, imagine that these two teeth were in contact, and as a result, right, we've got a contact force. Well, that contact force is tangent to this same circle. So here, FC is the contact force. It has some magnitude, and it's in the normal direction, which we'll call N plus. Then, on the corresponding mating gear, well, we have the same contact force, right? And that force, if we take a similar profile for the gear, that force is tangent to a circle that corresponds to the second gear. So here, this one is going to be FC, same magnitude, and normal to the gear tooth profile. So what? Well, if the contact normal is tangent to the radius r, and here, let's say that the radius of this circle is r, then the contact force magnitude is constant, right? So if Tn is the magnitude of the input torque, then that's going to be balanced out by this moment produced by the contact force. So that's going to be R times Fc. And it really doesn't matter where this contact point occurs because the radius is always the same. If the input torque is constant, then the contact force is constant. Looking at the second gear, if each gear tooth has this property, namely the normal is always tangent to a constant circle radius, then T out is constant, just like we wanted, right? Because Tn is constant, the contact force is constant, right? So over here, the contact force acting on the output gear is constant. The radius is constant, which means that the output torque is constant. So we have T out divided by Tn, so the ratio of torques. And this is from an earlier lecture when we were looking at the kinematics of gears. That implies that the ratio of angular speeds is constant as well. Now, these curves are known as involute curves. So the tooth profiles, again, they're known as involute curves. That's the shape of this tooth profile that we have drawn here. So how do we construct these curves? Well, there's actually a really kind of nice physical geometric interpretation. So imagine that you had a circle and you had a string wrapped around it. And then you take that string, right? So the string is wrapped, it's constant length, right? So you take that string and you just pull it off. Well, here, the path from the end of the string is exactly an involute curve. How do we see that? Well, the normal to this involute curve is going to be directed along the string, like so. And because we're pulling this string off of the disc, then it's going to be tangent, right, at some point. So here for the yellow curve, as we start to pull it off, it's tangent here. As we pull it off a little further, right, the point of tangency moves over to here. And then finally, as I move to this green configuration, the point of tangency drops down here, right? But this curve, the involute profile, always has a normal that's in the direction of the string and therefore tangent to this curve. Right, so the normal to an involute curve, right, so that's going to be represented as N, is in the direction of the string as we pull it off. It's always going to be tangent to the base circle. And this base circle has radius rho. So in particular, if I look at this sort of final configuration, this vector, right, from say O to maybe C, where the string is tangent, it's going to have length rho, because that's the radius of the circle, and it's going to be in this tangent direction. And then the contact force will be in the normal direction. As a result, the moment produced about the center of what will be the gear by this contact force is, well, so it's going to be rho in the t direction cross Fc in the normal direction, which ends up being rho times Fc in the k direction. And again, this is independent of where the contact point is. And this is really the important part. So if this force was anywhere on this involute curve, the moment would be rho times Fc. Now, finally, the last interesting property is that the distance from the involute curve to the base circle is actually relatively easy to determine. So again, if I want to know the length of the string that I have pulled off the circle, so that would be from here to, say, here. Let that be S. Well, it's going to be the length of the curve that was on the cylinder. Right? So it's going to be this length. And this length, if this angle is phi, this length is rho times phi, right? So this is rho times phi. So really the angle from the base of the involute curve to where this tangency is determines the length of this part of the string. So we're going to make our gear tooth profiles to be involute curves. Let's look at a couple of gear tooth characteristics. Here I've shown a gear, and I've shown part of a gear, right? Maybe 4 teeth. And let's say the center of the gear is here. We can identify a number of different kind of important measurements. One is the pitch circle, right? So that's, if you think back to our initial discussions of gears, they're like ideal gears are like circles that are tangent, right? So the pitch circle radius is the radius of that ideal gear, right? So maybe from here to here, right? So that's going to be R. And with that, we also have what's known as the circular pitch, and that's the distance between the teeth as measured on the pitch circle. Right? So if I look at this distance is defined as P, again, the circular pitch. Now, another important measurement is that of the base circle. So we have to generate these teeth, and we do that based on that base circle radius, right? So it's the generating circle for the involute teeth profiles. And there, right, essentially we have something like this. Right? So this is going to be rho. Rho is going to be the radius of that gear. And as a result, we have the distance between teeth as measured on the base circle. Right? So that's going to be this distance. And that'll be defined as PB as the base pitch. So again, the base pitch is the distance between teeth as measured on the base circle. Circular pitch is the distance between teeth as measured on the pitch circle. And then finally, we have a couple of other measurements. We have the addendum, which is the distance from the pitch circle to the top of the teeth. All right, so we'll call that A. And then we have the dedendum, which is the distance from the pitch circle to the bottom of the teeth. And that'll be D. Notice that the dedendum can actually extend below the base circle if needed, but we don't want contact to occur there because we want the contact to follow the involute profiles that we discussed earlier. One important thing to keep in mind here is that the pitch circle and, as a result, the circular pitch depend on the gear pair. Right? So it depends on how the two gears that are in mesh fit together. As a result, they cannot be physically identified or determined from a single gear. Or from an isolated gear. The other quantities, though, right, we can just pick a gear up and we can measure them. Right? We can figure out what the base circle is and the addendum and the dedendum. Right? But again, the pitch circle and the circular pitch, those are only specified, only determined once we put two gears in mesh. So now let's look at really what happens as a pair of gears are conjugate. So as we said, the contact normal, it has to be tangent to both of the base circles, right? Because both tooth profiles are composed of involute curves, right? So as a result, what we find is that the only location that we can have contact must be kind of along this line, right? Because this is the line where the direction is tangent to both the base circle of gear 2 and the base circle of gear 3. And that's known as the pressure line. Right, so all the contact occurs on this line of action. Now, notice that this line of action, the pressure line, is inclined at some angle. And that angle, actually, is known as the pressure angle. And it's given by phi. Also, phi ends up being that angle and that angle. So for a given pressure angle, right, all three of these must be identical. Right? So the pressure angle represents the inclination of the pressure line. While, again, the pressure line is the line of contacts, or the line of contact points. Finally, we have the pitch point, P. So that ends up as the ideal point of contact between the two gears. Right? So if you think about them as circles that are tangent and in contact, then the pitch point is the place that those ideal gear radii come in contact. So we actually have a little bit of geometry here. Notice that the pitch point is a distance of R2 from the center of gear 2, and a distance of R3, and a distance of R3 from O3, right? Because those are the radii of the pitch circles. So looking at, essentially this triangle, right here, here, and here, that's a right angle. We find that rho is equal to R times cosine of phi. And this holds for both gear 2 and gear 3. And from our previous description of gears, the module, right, or essentially the distance between teeth, has to be the same for gear 2 and 3, right? So looking at the module for gear 3, it's 2 times R3 divided by N3, right? The pitch distance actually has a factor of pi here, but we see that for gear 2, it's 2R2 over N2. Or in terms of the base circle radii, we end up with 2 times rho 3, because R here is rho over cosine. So cosine times N3. And for gear 2, we have 2 rho 2 divided by cosine of phi times N2. Looking at the left and the right, we see that rho 2 divided by N2 must equal rho 3 divided by N3 if the gears are in mesh. This is actually kind of nice because these are now quantities that we can measure, right? So if you have a gear, you can calculate the base circle radius divided by the number of teeth. If you want to know, does that gear mesh with this other gear that I have? Well, go and look at that ratio for the other gear. If they're the same, then those two gears can mesh together. If those two quantities are different, though, then those two gears are not able to be in mesh. You would end up with interference, and the gears would bind and lock up, and those gears would not rotate freely. So this is kind of a fundamental compatibility condition for two gears in mesh. Now, the last thing that we'll notice is that if the center distance is known, because after all, these R's depend on the distance between O2 and O3, right? So if we know the center distance as D, which is R2 plus R3, and I'll just note that this D is the distance between O2 and O3, not to be confused with the addendum that we talked about before. But if the center distance is known, then we can write that actually in terms of the base circles and the pressure angles. Or rho 2 plus rho 3 divided by cosine of phi. As a result, we can actually solve for the pressure angle given the center distance and the base circle radii of the two gears in mesh. Right, so oftentimes gear designers will specify a pressure angle, and then that might determine the mounting distance between the two gears in mesh. One more quantity that ends up being relatively important is the contact ratio. So if I look at this picture on the right, what I've drawn here is a single pair of gear, or a single pair of teeth, in two different configurations. Right, so the configuration on the lower configuration is when the red and the purple gears first come into contact. You know, maybe things are rotating kind of in this way and then in that way. And then they leave contact at this upper position. Looking at the distance between teeth, that was given as the base pitch. So the distance between and this is the distance between teeth on a individual gear. Right, again, that's PB. So it's 2 pi rho 3 divided by N3. Right, that's the circumference of gear 3. Right, that's the number of teeth. And that, of course, had to be equal to 2 pi rho 2 divided by N2, circumference of gear 2, divided by the number of teeth, while this pair of teeth engage at this point. We'll call that point A, and lose contact at point B. So these teeth engage at A and lose contact at B. I want to know the length of that interval. Well, once again, we have the pressure line, which in this case essentially looks like here, and then extends all the way down, right? But this solid portion is the interval that the teeth are in contact. We'll define this contact interval so we'll define it as delta AB. The contact ratio is abbreviated as CR, and that's the ratio of the contact interval, or the distance over which a pair of teeth are in contact, divided by the distance between teeth on an individual gear. So here, if I look at this, the distance between teeth is relatively easy to calculate. The contact interval is a little more difficult, right? But not too bad. We can break this up into the distance from A to P plus the distance from P to B. Well, when looking at the distance from A to P, we're actually going to look at gear 3. And what we'll do is we'll calculate the distance from this point where the pressure line is tangent to the base circle out to A. And actually we can do that because we know this radius, this is a right triangle, we know this side, right? So if you think about this big triangle that kind of extends off to the right, then we have hypotenuse, adjacent, opposite. So the opposite side is the square root of the hypotenuse, R3 plus A3, minus the adjacent side, right? So rho 3 squared. And then we'll subtract from that the distance from this point to P, right? So that's going to be R3 squared. Now we're looking at this triangle where R3 is the hypotenuse minus rho 3 squared. And so that's the distance from A to P. To that, we will add the distance from P to B. And with that, we'll do the same thing over on kind of looking at this triangle formed with gear 2. And that's R2 plus A2 squared minus rho 2 squared, and then minus R2 squared minus rho 2 squared. Like I said, a lot of stuff here, but these are things that we can calculate. We can actually calculate them relatively easily. So we have the contact interval, we have the distance between teeth, and we just take the ratio to find CR, contact ratio. Why is that important? Well, here it is. The contact ratio, it represents the average number of teeth in contact. And clearly, we want the average number of teeth to be greater than 1 for continuous engagement. If at some point the number of teeth in contact drops to 0, that's bad, right? Because that means the teeth are no longer engaged. Let's look at this a little bit. Well, the contact teeth engage at intervals of P sub B, right? So again, that was the base pitch. Here, I've drawn the number of teeth in contact for a single pair, right? So you can think about, we just have 2 teeth, one on each gear, and they come into contact at 0. So here the horizontal axis is sort of units of the base pitch, right? So they come into contact at some arbitrary point. We'll call it 0, and then they stay in contact for an interval of delta AB, right? So, and here the contact ratio is 1.25 for this example. So delta AB is 125% longer than PB, right? So they stay in contact for a while, and then they lose contact again, right? So again, thinking back to this picture, right? They came into contact, and then they stayed into contact, and then they left contact, right? And then there's a long period of time as they circle back around that there's no contact. So, however, at this next interval of the base pitch, there's actually another set of teeth that come into contact, right? So that set of teeth they're not going to be in contact for a while. And then here, they're actually going to be in contact, and they're going to stay in contact for, 1.25 times the base pitch. And likewise, right, there's actually going to be another set of teeth, right, that comes in and is later in contact, and then they would actually stay in contact a little bit later. In fact, if you look previously, before this green set of teeth were in contact, there was actually a set of teeth that came in contact over here, right, and kind of stayed in contact for a while, and then dropped out of contact. So you constantly got teeth coming in and out of contact. Well, if you look at the total number of teeth in contact, right, and actually I'll start here. We just have 1 tooth. We had this red pair. But now suddenly we have 2 teeth in contact. But as the red pair drops out, right, then we only have 1 pair of teeth, right? But now the pink teeth engage, and then now the orange teeth engage, right, and so forth. In fact, if you go back in time, right, there was another set of teeth that, right, lost contact way over here. So what we have is the following. The number of teeth in contact must be an integer. All right, so it's 1, it's 2, it could be 3, something, but it has to be an integer. But because they don't stay in contact for sort of full multiples of the base pitch, we can get contact ratios that are not integers, right? So again, it ends up being the average number of teeth in contact. So if you see a contact ratio of 2.3, right, that means that you always have 2 teeth in contact, and occasionally you have 3 teeth, right? And then it comes back and drops down to 2 again. Kind of like in this example, we had a contact ratio of 1.25, right? So it kind of bounces around between 1 and 2. And as a result, the contact force, All right, so the net contact force is shared between teeth in contact at any instant. Right, so again, this contact ratio, it's really kind of important for looking at things like the stress that a gear tooth would face, how the load is shared across the gears, lots of different reasons. But so that's our quick introduction to tooth profiles. There's actually a lot more that goes into designing teeth. We haven't talked about the width of the tooth. Certainly things like stress concentration factors can be important. Right? There's a lot of stuff that goes into proper gear tooth design. But this is a quick overview of just some of the basics. Things like contact ratio and circular pitch and base pitch and all of that kind of stuff. So that's it for now. Thanks, and I will talk to you again soon. Take care. Bye.